So it is my pleasure to introduce Kyle Zarzana from CU Boulder right now. He's working with Rainer Volkamer as a postdoc. I just knew that. It's interesting. Kyle got his PhD at CU working with Maggie Tolbert, actually working on aerosol optical measurements using cavity ring down and photoacoustic spectroscopy. And then he went to NOAA, and then he worked as a postdoc with Steve Brown working on Glyoxal measurements and measurements of nocturnal nitrogen oxides. I think he's going to present something about that and emissions of Glyoxal.
Thanks, Ivan. So I'm going to talk about work that I was doing at NOAA on Glyoxal and Methylglyoxal emissions from biomass burning. So why do we care about these two molecules? This is Glyoxal here, and then this is Methylglyoxal here. So there's been some work suggesting that Glyoxal is a source of aqueous SOA and potentially brown carbon. This is a figure from Christopher Knote's paper, a mechanism for getting Glyoxal into aqueous aerosol and then reacting with ammonium, which can form brown products. And then Methylglyoxal, once it photolyzes, it can go on to participate in the formation of PAN. Both of these molecules, if they photolyze, can form radicals that can influence ozone production. So this is data from Pete Edwards' work looking at wintertime ozone formation in the Uinta Basin. And there, a lot of the radicals that kicked off the ozone formation came from the photolysis of formaldehyde, Methylglyoxal, and Glyoxal. And there's been some evidence from modeling work that the photolysis of these molecules, formaldehyde, Methylglyoxal, Glyoxal, can play a role in ozone formation, biomass burning plumes. Glyoxal and formaldehyde can both be detected from space, from satellites, and they have very different VOC sources, but they have roughly the same lifetime in the atmosphere. And so it's been proposed that you can use this Glyoxal to formaldehyde ratio, RGF, as a marker for VOC oxidation and try to examine that from space. So this is work out of Frank Koich's group. This is OMI data looking at the Glyoxal to formaldehyde ratio over the US. And you can see there's regional differences. In the southeast here, where there's mostly isoprene, this RGF is very low, and it's higher in the northwest US. And this is another look at the OMI data from Christopher Chan Miller. This is a global map of RGF in the summer months. And this regional gradient in the US is a little less obvious because there's these very high RGF values in areas that are influenced by biomass burning, such as in Africa and South America. And looking at the budgets for these molecules, biomass burning and biofuel use are believed to contribute about 20% of total Glyoxal emissions, but only 4% of Methylglyoxal emissions. Unfortunately, these budgets are very old, and they're based on pretty old laboratory studies. There's only 2 previous laboratory studies of Glyoxal emissions from biomass burning, and they're from 2000 and 2002, and they both used a very non-specific method. It's based on the EPA method for measuring formaldehyde, and what they did is they passed fire emissions over cartridges coated with dinitrophenylhydrazone, or DNPH. And so DNPH does this chemistry with anything that's got a carbonyl group, forms some product that absorbs in the UV at around 340 nanometers. And then they tossed this product into a UV vis and said anything that came out at a certain retention time and absorbed, that must be Glyoxal. And this method is really not a good idea for using in biomass burning. This is work from the 90s looking at interferences with this DNPH method. And it's a little hard to see, but there's actually 2 peaks right here. There's one in the solid line and one in the dashed line. One of them is from the product of formaldehyde plus DNPH, and the other one is from NO2 reacting with DNPH. And there's also ozone interferences with this method. And so this is data from a laboratory study that we did that I'll talk about in a few minutes. This is NO2 in blue and formaldehyde in red. And you can see their concentrations in the fire are actually pretty comparable to each other. And the data from these papers suggests that the Glyoxal to formaldehyde ratio from biomass burning should be approximately 1 in the molar sense. And we just don't see that in the satellite data. And so we wanted to go do a better job with this. And so the instrument that I use is called ACES, the Airborne Cavity Enhanced Spectrometer. This is a picture of the inside of the box. The way this works, we filter particles. We measure wavelength resolved gas phase extinction in 2 channels. There's a UV channel from 360 to 390 that gets NO2 and HONO. And there's a blue channel from 440 to 470 that gets NO2, Glyoxal, and Methylglyoxal. So a little instrument schematic down here. We've got an LED centered at 455 nanometers. It gets coupled into this high finesse cavity. The light makes a bunch of passes due to these highly reflective mirrors. And we end up with an effective path length between 10 and 20 kilometers. So it's a very sensitive measurement. And then the light that leaks out the back of the cavity goes through a grating spectrometer and then gets imaged onto a CCD. So to do these fits, we have this wavelength resolved extinction. And this is just some data that I made up just to see what it looks like. It's easier for a presentation. So this is our measured spectrum. We have literature cross-sections. In this case, it's just NO2 and Glyoxal. And then we find the linear combination of these two cross-sections that fits the measured spectrum. So if you just use NO2 in the fit, you can fit these peaks on the edges of the spectrum, but you don't get this peak in the middle. And then if you add in different amounts in Glyoxal, you can find concentrations of these two species that give you a nice fit for the spectrum. And so this is just some example data. The blue are the measured concentration, measured spectra, and then the red are the fits to these. So this is HONO from the UV channel, this is NO2 from the blue channel, Glyoxal from the blue channel, and Methylglyoxal from the blue channel. So because we're using the whole wavelength range, we get a very specific, very selective measurement, and with that path length, it's very sensitive. So I'm going to be talking about biomass burning in this, and I want to cover a few biomass burning terms that might not be familiar to everyone. So the first one is the emission ratio, and it's the background corrected mixing ratio of some species X divided by the background corrected CO mixing ratio. And this is reserved for measurements just made at the source. So there's no chemistry, this is just straight fresh emissions. And to get this, you can either integrate over the course of the fire, or you can look at the slope of Glyoxal, in this case Glyoxal versus CO. And so this is some data from the lab experiment that we did. Another term that's very similar to emission ratio is normalized excess mixing ratio. It's the exact same equation as emission ratio, but you can measure this anywhere. So if you're out in the field and you're measuring some plume that's maybe aged a little bit, this is the term you would use for what you measured there. Other common term for this biomass burning is emission factor, and it's the grams of a compound emitted per kilogram of fuel burned. And when you're out in the field, the way you do this, get the amount of fuel burned, you sum all the measured carbon-containing species and you assume some carbon content in the fuel. And this generally works pretty well. Most of the carbon comes out as CO2, CO, and methane. Somewhere between 90 and 95% are in just these three species. And the last term is the modified combustion efficiency, or MCE. And this is a proxy for fire stage, whether the fire is flaming or just smoldering. And the MCE is just background corrected CO2 divided by background corrected CO2 plus background corrected CO. And an MCE of 0.9 means the fire is about half flaming and half smoldering. And an MCE of 1 means you have a purely flaming fire. So we have some field observations of Glyoxal and biomass burning plumes. ACES was on the NOAA P3 for the 2013 SENEX campaign in the Southeast US and the 2015 SONGNEX campaign that was out of RAF. And neither of these campaigns were specifically focused on biomass burning, but both of them did intercept some biomass burning plumes during the course of that. In 2013, my predecessor at NOAA, Kunyun Min, who actually designed and built this instrument, was running the instrument, and then I was running ACES in 2015. And so in 2013, we had 10 nighttime plumes and 5 daytime plumes. This is a picture that Yost took of one of the daytime plumes. It's a little ag field that's on fire. And then in 2015, we had 2 daytime plumes. This is a sugarcane field that was burning in Florida during the SONGNEX test flight. So I'm going to focus in on one of the particular flights we did during SENEX. This was a night flight. The idea was to look at power plant plumes at night, but when they went into this area here down by Missouri and Kentucky, they ended up seeing biomass burning. If you look on the satellites, there was a lot of fires that were detected in the days before and after the flight in the northwest of the flight track here. And the wind was coming from the northwest, and so we ended up seeing several biomass burning plumes. So this is the flight track colored and sized by Glyoxal concentrations. And this is just some sample data from one of those plume intercepts. Got NO2 and ozone. You can see the ozone being titrated out by the NO2, methane, HONO, Glyoxal, formaldehyde, CO, and CO2. And then over here, I have plots of Glyoxal versus CO and Glyoxal versus formaldehyde. And so in this plume, we had about a ppb of Glyoxal per ppm of CO emitted, and only about 3% Glyoxal relative to formaldehyde. So these are the data from those 2 previous lab studies and the number that was used in the Glyoxal global budget. So this is Glyoxal versus CO on the top, and then here, this is Glyoxal versus formaldehyde. So those lab studies, like I said, saw a Glyoxal to formaldehyde ratio of about 1. And when that number was put into the global budget, they ended up using about 7 ppb Glyoxal per ppm of CO that was emitted. And we see something very different in the field data. Very low Glyoxal to CO emissions and about 1.6 ppb Glyoxal per ppm of CO. and very low Glyoxal and formaldehyde ratios compared to what the laboratory studies saw. So they saw about 1, and we see about 5%. There are some caveats to this. We didn't know the fuel type for any of these fires except for the one that was sugarcane. And we also didn't know the plume ages. On a lot of these fires, a lot of these flights, we didn't see where the fire was. We just saw evidence that we went through a biomass burning plume. Glyoxal is pretty reactive, can do aerosol uptake, and there's also gas phase chemistry that happens in these fire plumes. This is a figure from some work out of Bob Yochelsen's group looking at formaldehyde enhancements downwind of fires. And they see very sharp increases in formaldehyde sometimes, other times they see very gradual increases. So there is chemistry going on in these plumes that could be making Glyoxal or destroying Glyoxal. And so looking at, again, that SENEX data, this is the flight track, and these markers here are all the biomass burning plumes. And again, the wind was coming out of the northwest. Fire was probably somewhere around here. And if we look at the Glyoxal to CO and Glyoxal and formaldehyde as a function of distance, from kind of an arbitrary point here in the northwest, we do see some correlation between distance downwind and the Glyoxal CO or the Glyoxal and formaldehyde. And in particular, these two red points are these 2 points here that are circled in black. And they're definitely, this point is downwind of this, and the time between the intercepts was roughly equal to the transport time based on the wind. You can see these do in the CO, Glyoxal CO increases, as does Glyoxal to formaldehyde. So there's hints that there maybe is Glyoxal production in these plumes. And so what we want to do is do another lab study on these Glyoxal emissions and try to do a better job than those previous groups had done. And so in 2016, about 2 years ago, we went to the Fire Sciences Lab in Missoula, Montana. It's a US Forest Service facility where you can study fire emissions pretty easily. So these are just some pictures that I took. The heart of the facility is this burn chamber. Right here is the burn platform where we actually lit the fires, and there's this big chimney that's pulling the air up to an instrumented platform about 16 meters above the floor. And this is a picture looking down from the platform onto the floor, and this is the chimney before we started cramming all of our instruments on here. So this is what it looked like after we crammed everything up there. There's a bunch of SIMs. There was Bob Yochelsen's open path FTIR right here, and then ACES was mounted right by the FTIR, sampling right off there. ACES was measuring NO2, Glyoxal, Methylglyoxal, and HONO. The open path FTIR was measuring CO, CO2, methane, formaldehyde, and a variety of other species. Because there was a weight limit on the platform and we couldn't cram everything we wanted up here, we had a heated transfer line down to the control room where we had a bunch of other instruments. We had the NOAA PTR TOF that was being run by Abby Koss, Matt Coggin, and Kanako Sekimoto, and then the CU I- SIMS that was being run by Ben Yuan. So we had a heated transfer line. This is Abby and Kanako installing the line. And then this is the line coming down from the platform to the control room. You can see it there. So the PTR and the I- were measuring a lot of VOCs such as formaldehyde. And then this is just the setup here again. So we had the fuel bed, it's pulling up the stack. It's a few second residence time, and the smoke, they've done tests. It's pretty well mixed by the time it gets up here. Open path FTR was measuring across the span of the stack. ACES was pulling right off, and then the PTR and the I- had the line over to the control room. One of the other problems with those previous lab studies is they only looked at a few fuel types, and in 2016 we ended up looking at a total of 33 different fuel types, and for that phase of the campaign we did a total of 75 burns. So we did chaparrals, so chamis and manzanita. We did conifers, such as pines and firs, and for the conifers we did several different types of burns. We did a realistic mix where we had approximately the amount of twigs and branches and leaves and litter you would find in the forest. We also did single component burns, so canopies, just the upper part, litter burns, duff. Duff is halfway between dirt and plant, basically. And then we also did a couple of rotten log burns. Did a few artificial fuels like Excelsior, which is these long, thin strips of wood that are used for packing or insulation. Did one untreated lumber, and then a few other ones such as peat, rice straw, and yak dung. And so this is just a video of one of the fires. This was a realistic mix of lodgepole pine. So there's two views of the fire here, and then this is the time series of Glyoxal on the bottom here. And you'll see a couple people in the room. This is Megan Dills, and then Ed O'Bannon is in the yellow off screen. And they're firefighters who normally are out fighting fires, but for this project, they're actually in the burn chamber for all of these burns, lighting the fires, and really made that part of the campaign go well. You can see right at the start of the fire, there's this huge peak in Glyoxal, and then some other peaks, but then it tends to die off as more of the fuel gets consumed. So I'm going to talk about the methylglyoxal emissions first. This was a very challenging measurement, both for our instrument and for other instruments. So there's a lot of other methylglyoxal's cross-section is down here in this orange, and it's not a very distinct cross-section. NO2 has lots of features with these peaks and valleys. Glyoxal has this nice peak here around 455. Methylglyoxal really doesn't have much. And there's other compounds such as 2,3-butane-dione, which is just methylglyoxal with a methyl group over here. And they have very similar cross-sections. So zooming in on those cross-sections, in orange is the methylglyoxal, and in pink is the 2,3-butane-dione cross-section. And if you increase it just by about a factor of 2, it looks very similar to the methylglyoxal cross-section. 2,3-butane-dione was measured by the PTR-TOF, and the concentrations were within a factor of 2 or so of the methylglyoxal concentrations that we measured with our instrument. The PTR-TOF does measure a signal at C3H4O2H+, the methylglyoxal mass, but there's another molecule there, propanoic acid or acrylic acid, that is going to show up at the same mass. The PTR-TOF signal there was calibrated with theory, and they just said it's an equal amount of methylglyoxal and propanoic acid. They didn't have a way of separating out those two. The I- SIMS also measures propanoic acid, and they did calibrate that by doing standard additions with liquid calibration unit after the campaign, but there's really poor agreement between these three instruments. So the ACE's methylglyoxal is here in the orange, the I- acrylic acid is here in the blue, and both of those are a lot bigger than the PTR-TOF signal at C3H4O2. So there's still a lot of work to be done on this measurement. What I did is I ended up using the 2,3-butane-dione that was measured by the PTR-TOF to correct our methylglyoxal, and that brings it down by about 20%. But they're likely to be underestimates, and there's a lot of uncertainty in this measurement. So these are the methylglyoxal emission ratios and emission factors that I got from the fire lab. And I've grouped them here not by species, but by the kind of burn that we did. So the chaparrals are here. All the realistic mixes are together, canopies, litter, duff, etc. Don't want to spend a whole lot of time, because like I said, there's a lot of uncertainty in this. Generally, within a type of burn, so realistic mix, they were pretty similar, and that mattered more than species. Comparing this to the global budget and the previous data, the emission ratio in the global budget actually did a pretty good job in terms of comparing to what we saw at the fire lab. It's a lot lower than it's a lot higher than the chaparrals, but it's pretty good agreement with the conifer and pines. And the red markers here are the previous literature data, and again, they got pretty close to what we saw at the fire lab. Looking at the ratio of methylglyoxal to glyoxal, we always saw a lot more methylglyoxal than glyoxal, in some cases to a factor of 20 or so. And this is very different than what was in the global budget. The global budget predicts that there's going to be less methylglyoxal than glyoxal coming out of these fires, which was not what we see. Turning to the glyoxal now, here are the emission ratios, again, grouped by fuel type rather than fuel species. And within these groups, generally very similar. Shown here in the shaded is the range of the field data, and what we were seeing at the fire lab is generally in pretty good agreement with those measurements we had during SENEX and SONGNEX. Again, we don't know the fuel type from those field measurements, but this seems to be in line with what we were seeing from the fresh emissions. And these are also, again, much lower than what was predicted by the global budget. They're up here around 7, and we're seeing about an average of 1.6 ppb glyoxal per ppm of CO. Down here are the emission factors. Again, pretty good agreement within a fuel type, and much lower than those previous laboratory measurements, excuse me. So we did see some scatter in these measurements, and I wanted to take a little closer look and see if there was anything that could tell us what's controlling that scatter to put that into a model. Two things I looked at are MCE and the moisture content, and MCE, remember, tells you the fire stage, so a higher MCE means it's a hotter, more flaming fire. Moisture content in this context is going to be defined as the wet weight minus the dry weight divided by the dry weight. So this is Glyoxal emission factors versus MCE for all the burns. I took out some of the more unique fuels like the yak dung and some of the rotten logs. And we generally see a pretty good correlation between emission factor and MCE. And this isn't very surprising. The hotter the fuel, the hotter the fire, the higher the MCE, the more of the carbon ends up as CO2. So this is what you would predict. For fuel moisture, this is all the fires versus fuel moisture. And if we look at just a subset, the same subset as before, we see a decent correlation between moisture content and emission factor. This also isn't super surprising. Fuels that are wetter tend to have a lower MCE just because they smolder more. And so it's hard to tell whether it's MCE that's driving this correlation or moisture content. For some of these other, again, just looking at the instantaneous emission ratios, this is Fire 16 and Fire 38, which are both ponderosa pine litter. They had very similar moisture contents, very dry fuels, very similar MCEs, but they had very different instantaneous behaviors. This is Glyoxal versus CO for these two fires. And the main difference is that in Fire 16, we were continuously adding fuel because we were trying to fill up one of the chambers that was there. And every time we added fuel, we got this different slope in the Glyoxal versus CO. In this fire, we only added fuel once, and we got one slope, and we ended up with two very different emission factors. So while there are some things like MCE and moisture content that can affect how much Glyoxal comes out, there's a lot of other things that can control those emissions. And this is another fire that I looked at. This was a rotten log burn. I don't want to read too much into this. Rotten logs are really weird just because there's not a standard for it. They can be more or less rotten. But here I've got a video of it, and then I've got Glyoxal versus CO, and it's colored by MCE. And so the hotter colors are higher MCEs for this burn. And so at the start, there's no flames, it's just smoke coming out. And we end up with one distinct Glyoxal to CO emission ratio at the start of the burn. And then as soon as the flames appear, we end up with a very different Glyoxal to CO emission ratio that's much lower than what we were seeing before. And what's interesting about this was actually the highest Glyoxal to CO emission ratio that I saw on any of the burns. And this was pretty low. And so we see this change in Glyoxal to CO emissions as the MCE changes and we go from not flaming to flaming. But we don't see that in the Glyoxal to formaldehyde ratio. That Glyoxal to formaldehyde ratio is consistent for this entire burn. Didn't matter what the MCE was, didn't matter what Glyoxal to CO was doing. Got one number here. And looking back on those two ponderosa pine litter burns, very different emission factors, very different behavior in Glyoxal versus CO, but very similar behavior in Glyoxal and formaldehyde. Only one slope, RGFs are about 25% different. And so again, we have the emission ratios and emission factors. There's some scatter in them, both between groups and within groups. But when we look at the Glyoxal to formaldehyde ratio for all these burns, they're generally very consistent. So chaparral and litter, which had very low Glyoxal to CO emission ratios compared to these realistic mixes in canopy, had almost the same Glyoxal to formaldehyde emission ratio. And some of these other burns didn't have different Glyoxal to formaldehyde compared to the canopy and realistic mix. Peat is still very low. It emits basically no Glyoxal relative to formaldehyde. And comparing this to the satellite measurements, so again, here's the ones we measure the fire lab. In the shaded is the range of the field data, generally in good agreement. The isoprene RGF that was measured in SENEX is down here in the blue, and we're much higher than that. This is about 2.5%, and we average 6 to 7%. This pink line here and this green line here are satellite RGF values. This is from Africa. This is over the North China Plain. We're in pretty good agreement with the Africa value, and we're a little bit higher than this NCP, this North China Plain, and we're gonna have to do some more work to understand those differences. There's a hotspot of Glyoxal over the Pearl River Delta that's mostly from aromatic VOC oxidation. That's a little bit higher than the Glyoxal to formaldehyde ratio we see from biomass burning. And of course, not to continue to pick on to those older studies, but I just switched to a log scale to put them on the same graph, and they're up here at 1, and this just makes no sense. So Glyoxal and formaldehyde, at least for our fresh emissions, 6 to 7% seems to be the number to use. So what does this mean for the global Glyoxal budget? So I hope I've convinced you that the emission factors in the budget for biomass burning are too high. However, there's some caveats to that. Fire inventories tend to miss a lot of small fires. This is data from Huang et al., and they looked at acreage that was burned based on permit data and based on satellites. So they did phone interviews with people who were out actually doing the burning, and they think that the amount of acreage that was listed in the permit is within 10 or 20% of the amount that was actually burned. And the amount from the permit was generally significantly higher than what was captured by these inventories, GFED and this other one here. So yes, the emission factors might be in the budget might be too high, but if the fire burned area has been way underestimated, then that might come out to about even. There's also the potential for secondary production of Glyoxal in these biomass burning plumes. In the budget, isoprene is the main source, but this was done in 2008, and there's been a lot of work recently on isoprene oxidation chemistry. And this budget only used one number for Glyoxal plus isoprene, and we know that's not right, that NOx has a really big impact on the Glyoxal production. So two different groups have looked at Glyoxal from isoprene from the SENEX data set, Li et al. And Chen Miller et al. And they both came up with very different answers for what Glyoxal production from isoprene should be compared to the MCE. So this is from Li et al., and they see very high Glyoxal production from isoprene when NOx is low, and that Glyoxal from isoprene decreases as NOx increases, which is the opposite of what the MCE sees. And again, Chen Miller sees something different. They see much higher yields in the MCE and different behavior with respect to NOx and OH exposure. So there's still more work we need to do in the lab looking at Glyoxal yields from isoprene and the effect that NOx is having on that. And then there's also been some evidence that there's a marine source of Glyoxal. So this budget only considered terrestrial sources, but if this is in there, then that's a huge source that we need to consider. And one last thing I was looking at before I left NOAA was looking at the carbonyl budgets in these fire plumes and how carbonyl photolysis could affect HOX and ozone formation. So I looked at carbonyls both from my measurements and from the PTR TOF. The top 5 carbonyls ended up about 80% of the total carbonyl concentration. So these are two pie charts. This is ponderosa pine and this is chaparral. And these generally representative of a lot of the burns we saw. Formaldehyde was always the top carbonyl, followed by acetaldehyde. Acrolein and glycoaldehyde switched between 3 and 4, and frequently methylglyoxal was number 5. And so the next step in this is obviously to get photolysis rates and look at the effect on HOX and ozone from that. So Glyoxal emissions of the fire lab were variable depending on the fuel type, and they were significantly lower than previously reported laboratory data, but generally consistent with field measurements. Glyoxal and formaldehyde were well correlated, and they're also consistent with field measurements, both from satellite and aircraft. And these RGF in biomass burning generally is very distinct from RGF in areas with large isoprene emissions. The weather is distinct from areas with more monoterpenes or aromatics remains to be seen. We also need to measure measurements of methylglyoxal or whatever this C3H4O2 is. ACEs doesn't do it well and the PTR TOF doesn't do it well. And those molecules are going to have different impacts on the atmosphere. And so future work, this summer I was working with Rainer Volkamer on the BB-FLUX campaign. This was from July to September 2018. We were on the University of Wyoming King Air. We did 37 research flights to 17 fires, and we were in Boise, Redmond, Oregon, and Provo, Utah. These are just some pictures from the campaign. This is from the C-130 inter comparison, and then these are several of the fires that we flew to. And this is our little crew selfie there. For the payload, it was mostly remote sensing instruments. We had 2 Zenith sky cameras in the blue and UV, and they were just pointing straight up and measuring scattered light. And from those, we could retrieve Glyoxal and formaldehyde columns using DOS. And I was running that instrument with help from Ted Koning, who's a grad student in Rainer Volkamer's group. And that Natalie Killa here was running the solar tracker. It's up here under the zinc selenide window that we borrowed from NCAR. There's an IR camera and a green camera, and their solar tracker keeps them pointing directly at the sun. And from the IR camera, we can get CO columns and various other IR active species. This is very, very preliminary data from BB-FLUX. This is 2 fires, the Rabbit Foot Fire in central Idaho. It started October 2nd, and it's actually still burning. It's in a pretty remote area, so they're just gonna let it burn out. And then this is the TP fire that started right after we got to Redmond. It only burned for a few days. And these are Glyoxal and formaldehyde columns that we retrieved for these 2 fires. And don't read too much into these numbers. There's still a lot of work that we need to do to finalize them. But as you can see, Glyoxal and formaldehyde are generally very well correlated Formaldehyde's generally about 10 times bigger, at least, than the Glyoxal measurements. And so this is something that I'm going to be working on for the next few months. And so with that, I'll be happy to take any questions.
Great. Thanks, Kyle. Are there any questions?
Nice talk, Kyle. So when you had the downwind production, I think it was Glyoxal, and do you think that's oxidation of glycolaldehyde or something else? Any thoughts?
There's a lot of things it could be. We tried playing around. Matt Coggin and I played around with the MCM a little bit, but I don't really believe the MCM because it doesn't get the SENEX data right. So it's hard to say. There's a lot of things that come out of fires that could be chewed up into Glyoxal.
Are there more questions? I just have a quick question. Why you didn't measure formaldehyde with the cavity? Is there a reason?
We don't get that far in the UV to get formaldehyde. The bands show up at 340 or so.
And Hono is at what?
So we cut out at about 360. So we can get a couple of the Hono peaks, but formaldehyde's, all the good peaks are down here.
Are there more questions? If not, let's thank Kyle again.